Hello everyone, thanks very much for attending my presentation. I'm Zhijie Zhang from Nanyang Technological University. I'm glad to present my research, Engagement Estimation of the Elderly from Wild Multiparty Human-Robot Interaction. Let's start from the background. With the development of social robots, deploying robots in the healthcare becomes a solution to providing medical and psychological care to the elderly. This has great impact as the proportion of people aged 60 years and older in the world will nearly double from 12% in 2015 to 22% in 2050, according to the WHO. Besides the basic conversation function, it is important to estimate the status of the elderly. In this work, we focus on engagement, which has been shown to play an important role in HRI. Here, engagement refers to the inner state of attributing to being together with others and continuing the interaction. If the robot can recognize the engagement state of the elderly, it helps the robot to respond to the elderly properly and maintain long-term interaction. Engagement estimation is kind of affective computing and behavior analysis, and it goes further to probe the inner intention. Conventional approaches use nonverbal cues such as proxemics, body pose, gaze pattern, facial expressions, and context information to build classifiers. Deep learning approach has also been developed recently. However, most previous work assumes that the interaction is in a laboratory environment or in a static situation. When the research is expanded to special population and more complex scenario, there are many challenges. For example, the nonverbal signal from the elderly alter in face shape and body behavior along with aging. Second, from static to multi-party human-robot interaction, understanding the dynamics of the interaction becomes more complicated. Third, in the wild space, moving people, bedletting, confusing objects, and so on makes it difficult to interpret the complex environment. Before explaining how we solve these challenges, let me introduce some concepts of engagement. In geriatric psychiatry, the measurement of engagement are well established. For example, the OME, which is one of the most well-known tools, and the EPWDS towards psychosocial activities by assessing the behavioral and emotional expressions and responses. However, all these methods requires expert involvement. In addition, engagement also contains several elements: behavioral, affective, visual, verbal, social, and cognitive signal. Note that these elements often overlap with each other, but in this work, our goal is to estimate the engagement of the elderly via a computer vision approach, so we pay more attention to behavioral, affective, and visual engagement. The verbal element is eliminated due to the input modality, and the cognitive, social elements are overlooked due to the participants' physical and mental conditions. To estimate the engagement of the elderly, we propose a deep learning method. It takes video clip as input and outputs the estimated engagement state. We first extract the behavioral, affective, and visual features. Then we feed these features into an individual learning modular. After that, the refined features are fed into group learning modular, which is an adapted graph attention network, learning the relationships among participants. Here is the architecture of the proposed network. I will explain the details of the feature extraction, individual learning, and group learning in next few slides. Feature extraction. We use ResNet 3D as a backbone to capture spatial temporal context of an input video clip. This is motivated by the promising performance of ResNet 3D models in a wide range of video-related benchmarks. The spatial temporal feature maps represent the behavioral engagement. We extracted 4 feature maps in time position. Meanwhile, we conduct multi-person tracking. We identify the main group members intuitively based on the frequency of a person's appearance and the distance from the camera. So given this, we use region of interest elegant to project the coordinates of the frame's feature maps and select all the corresponding feature for everyone. To extract the affective and visual engagement feature, we first perform multi-phase detection within the body bounding box. The detected phases are used for affective and visual feature extraction. Specifically, we employ a pre-trained ResNet 18 emotion recognition model to represent affective engagement, and we use OpenFace to extract the visual feature. Head pose, gaze directions, gaze angles, 2D eye region landmarks, and 3D landmarks are extracted, which together form the visual engagement feature. Individual learning. For the behavioral feature extracted in the previous modular, although they are localized to the bounding box, they lack detailed body posture and action information, so we introduce a self-attention mechanism to refine the behavioral feature. We hope that the attention mechanism can learn the interaction between any two feature positions in spatial temporal dimensions, which means focusing more on the important body regions in the spatial domain and the critical frames in the temporal domain. In our implementation, the self-attention mechanism is a non-local operation, as shown here. For affective and visual feature, because of the small feature dimension, we do not apply self-attention mechanism on them. Instead, we simply add an average pooling to make affective and visual feature have appropriate size. So finally, we concate these 3 individual features and reorganized it according to the detected people. Group learning. In a wild dynamic multi-party interaction, each participant plays a specific role. We define the main interaction group to be composed of speaker, addressee, and set participants. The rest, who may be bystander and overhears. In addition, in the elderly nurse-robot interaction scenarios, nurses are the people who are in daily contact with the elderly, and hence they have the prompt judgment about the expression from the elderly. These judgments are conveyed in their behaviors. Therefore, we hypothesize that analyzing all participants in the main interaction group and their relationships helps to estimate the engagement of the individual elderly. To represent the main interaction group, we propose to use the graph structure where each node corresponds to a participant and stores his or her feature map, and each edge represents the interaction between the participants of the 2 nodes. We adapt a 2-layer graph attention network to learn the underlying interaction between nodes by computing attention weights for each edge. First, we apply a learnable transformation parameterized by a shared weight matrix W to every node feature Hi to obtain a hair-level feature. Then, we compute the score of attention Eij from node J to node I, where A and B are the weight vectors to be learned. Here A1 and B1 are for the attention from any node to node 1 only, which is the elderly node, and A2 and B2 are shared for all other situations. This special design is due to the fact that the elderly is the main participant among all the participants in the group. Next, we generate the normalized weights that used to compute the new node feature as a linear combination of all the old features. To stabilize the learning process, we employ multi-head attention, where K independent attention mechanism resulting in K different Hi prime. Then we The new features of the eyes node from every head are concatenated to derive the updated node feature GI, which is the output node feature for the first graph attention layer. Finally, repeat this process in second layer. The only difference is using average instead of concate to get the final output. Experiments and results. To the best of our knowledge, there is no publicly available labeled dataset for learning the elderly robot interaction, not to mention that in a multi-party scenario. We used the BHEH dataset, which is collected by our colleagues. The elderly talked to a socially intelligent robot, while the nurses occasionally provide help. Moreover, the dataset was collected in a wild, dynamic, and multi-party environment. Here are 3 sample interaction sessions. We manually annotated 43 interaction sessions. The length of the videos are between 3 to 38. The number of participants for each session is from 1 to 6, and the label of the data is the engagement score, which was obtained by normalizing the EPWDS value to 0 and 1. So each interaction session was annotated by at least 2 experts. We sampled the videos by selecting 1 frame from every 5 frames and set 32 frames as the trunk size. As a result, each video clip is about 10 seconds. We conduct a 5-fold cross-test to evaluate our model. In individual learning, we use a non-local block with embedded Gauss bottleneck. In group learning, we use 2-layer 3-head graph attention modulus with hidden size, dropout rate, and slope as shown here. We train our model in 2 stages. The individual learning modular was trained first and then fine-tuned the network including the adapted GTA modular. The MSE loss, which is the mean square root error, is used in the training process. For evaluation, we use MSE and also MAE, which is the mean absolute error, because they are 2 widely used criteria for visual regression tasks. We attempt to compare our proposed method with the state of the art. However, there are no publicly available dataset or benchmarks for our problem. Thus, we took a compromise approach by applying their method to our dataset. It should be noted that the method we compared with do not publish their codes, so we implemented them ourselves. The main results are shown in Table 1 and Figure 1, so the performance of our method outperforms others. We also ran a number of ablation studies. We found that the result of using single element are worse than multi-element method. The self-attention modular and the GATs also helps improve the performance, which means the signal from set participants contribute to the estimation of engagement in multi-party scenario. For the comparison of ordinary GAL and our adapted GAL, we found that the adapted model achieves better result. Here are some visualization examples. It can be seen that our method achieves very good result. In conclusion, we propose an automatic method for analyzing wild multi-party human-robot interaction videos and estimating the engagement state of the elderly. The method adapts pre-trained models to extract the behavioral, affective, and visual features of the participants in the main interaction group. A supervised model consisting of a self-attention network for individual learning and a graph attention network for group learning is designed, and our method can effectively predict the engagement and outperforms the peer art. That's all for today's presentation. Thank you very much.